All right, so how is it that we assess or measure intelligence? Well, kind of any way we want because we get to make up what intelligence means. But, there are some ways in which we have identified as being like, these are established ways for us to assess intelligence. I want to start with the schoolhouse or the schoolyard logic of my brain is bigger than yours and examine that for a minute. So here's a question. If we're trying to assess intelligence, does brain size matter? So first of all, is it true that that Einstein had a big brain, and does it matter? Now, despite the fact that you are probably recognizing that this is an argument that was first developed by 3-year-olds, it turns out that it's actually true. There is a correlation, but you have to take into account body size, right? So it's a percentage, like how big is your brain compared to your entire body size? And if you look at that ratio, there's a correlation between brain size and intelligence, and it's not small. It's 0.33. That's actually an impressively large correlation. And it did turn out that Einstein's brain was about 15% larger, particularly in the parietal lobe region, which happens to be a center for processing spatial ability that seems to get recruited in complex math and physics problems. So it kind of matters. You know what? But yeah, 3-year-olds, sometimes they get stuff right. So here's another way that we can look at assessing intelligence. The last one, looking at brain size, that's like structure, right? Like, let's look at the structure of the brain and just see how big it is. Here, we can actually also look at function, right? Like, how's the brain working? Forget the size for a minute. And so this is referred to, this problem that you're seeing here is referred to the Raven progressive matrices, the Raven's advanced progressive matrices. And what you see here is this sequence of 8 patterns, and then you're as a participant, you're meant to guess what is the 9th item that would complete this pattern that's being generated. So the participants need to look at these specific examples in the first couple of rows in order to try to extract a general rule and apply it to identify what that missing piece is. And Heyer et al. Found that there was a negative correlation between scores on the Raven's progressive matrices task and brain glucose consumption. That is, the better people did on this experiment or this task, the less glucose that their brain needed to consume. That's actually sort of counterintuitive, right? It might seem like people who are really good at this task, their brain would be working particularly hard, but you can actually kind of think of this in terms of like physical effort, right? So people who are like have giant biceps find it absolutely no effort whatsoever to sort of pick up big piles of, like, I don't know, whatever, heavy things, right? Whereas people like me with very tiny biceps, I find it such a struggle to lift things. So I'm going to be working really, really hard, even though I'm really, really bad at lifting things. Same thing here, basically. So your brain is working really, really hard, but you're not very good at it. So that's why there's this negative correlation. Here's another test that looks at function. You can actually measure speed of perception to get an estimate of the speed of neural processing. That is like, it gives you like a general idea of how fast a person's brain works, essentially. So in this task, what you need to do is decide if the longer side is on the left or the right. So we'll look at 2 trials and then I'll break it down for you. Left or right? Another one? Left or right? So in this task, what's happening is the onset of the target is the object that actually has the longer side. And then you add a mask over top of it. And the mask stops perceptual processing, or stops neural processing of perceptual information. So by varying the time interval between the onset of the target and the onset of mask, you can get an idea of how fast somebody's perceptual processing is. And like the shorter that time span, and they're still capable of telling which side the target is longer on, the faster their perceptual processing and the faster their neural processing in turn. So people whose brains require the least inspection time to register the target tend to score higher on intelligence tests. So this is actually sort of what lets you, it's a little bit of a proxy, or it kind of stands in the place of a much longer, more involved IQ test, which is what the Wechsler Adult Intelligence Scale is. It's the most widely used intelligence scale today. And the WISC includes between 12 and 15 subtests, actually. So these are the subtests, and they actually break down into verbal comprehension, working memory, perceptual organization, and processing speed. But then you can further group them together so that there is like a verbal IQ score and then a performance IQ score. And then you can also combine that to get a full scale IQ score. So the benefit of the Wechsler Adult Intelligence Scale is that you can get this one number, which helps to give like a quick summary of a person's overall intelligence. But then you can also get these subscores, which give you a little bit more detail to dig into the specific abilities that a participant or a person is exhibiting. Now, the WISC is standardized. And what this means is that, so most IQ tests, like any good IQ test, is going to be standardized. So what this means is that the actual scores end up getting Z-scored. So they get forced into this normal distribution where 0, or like the Z-score of 0 is the mean. And what that means then is that your score on either side, like whatever the score ends up being, tells you the Z-score is like literally the distance from the mean in terms of standard deviations. So if your Z-score is 1.25, it means that you scored 1.25 standard deviations above the mean. And so what that does is it very quickly gives you a snapshot of where you land in terms of the entire population. So instead of using Z-scores, though, researchers and clinicians have used IQ scores. So it's 100 tends to be that mean. And deviations, so 100 Okay, buddy, thanks. Yep, gotcha. Be quiet. The WISC is standardized because IQ tests are standardized. I mean, reliable, good ones are going to be standardized. So what that means is that you can get a really quick snapshot of where somebody lands in the population based on their IQ score. And I can show you this by talking about Z-scores. So you know that between about 68% of the population fall within one standard deviation of the mean. Well, I can transform. I can just use a mathematical formula to transform data. So for example, like midterm scores, I can use a simple math formula that will allow me to translate that into, I can set the mean to be 0, and then I can set the scores so that it's how far you are from the standard deviation. So instead of scoring 78% on the midterm, that would be translated into about a 0.95 on this scale. And what that tells you is that the person scored about 0.95 standard deviations away from the mean or above the mean. So it gives you a really quick and easy way to compare people. So with IQ tests, Most IQ tests are standardized so that 100 points is the population mean. And that means that, and 15 points in either direction, it's either 10 or 15 points in either direction, is the standard deviation. So if a person scores 110, has an IQ of 110, it means that they have 10 points above the standard deviation or above the mean, but it's less than one standard deviation away from the mean. So you would say that that person is normal. That person doesn't have a particularly high IQ. So standardizing scores helps us to quickly and easily interpret IQ tests.